Hello there, and welcome. I'm so glad you found your way here tonight. Perhaps you've had a long day, or maybe you're simply the kind of person who likes drifting off to sleep while learning about the hidden wonders of our planet. Either way, you've come to the right place. Tonight we're going to descend together beneath the waves, past the sunlit surface waters where dolphins leap and seabirds dive down into a realm that most people never see and many don't even know exists. We're traveling to the ocean's twilight zone, a vast layer of water that wraps around our entire planet, holding more life than almost anywhere else on Earth, yet remaining largely mysterious and unexplored. This is the Mesopelagic zone, and it begins where sunlight starts to fail. It's a place of perpetual dusk, where the last faint rays of the sun create an eerie blue darkness, and where creatures have evolved in ways that seem almost alien. Some produce their own light in the blackness. Others have eyes the size of their heads to capture every precious photon. Many rise and fall through hundreds of meters of water every single day in what scientists call the largest animal migration on Earth. And all of this happens in a layer of ocean that accounts for roughly 1/5 of all the water in the seas, stretching from about 200 meters below the surface down to 1,000 meters, encompassing depths that would swallow most skyscrapers whole. You don't need to do anything but rest. Let your muscles relax, your breathing slow, and your mind drift as we explore this hidden world together. We'll meet creatures with names like bristlemouth and dragonfish, discover how millions of tons of life move through the darkness each night, and learn why this cold, dim layer of water might be one of the most important ecosystems on the planet for regulating our climate. Some of what you hear tonight might surprise you. Much of it remains mysterious even to scientists, but all of it speaks to the incredible adaptability of life and the vast unknowns that still exist in our oceans. Before we descend into the depths, if you find this journey relaxing, consider subscribing so you don't miss future explorations. And if you're still awake enough, let me know in the comments where in the world you're listening from. Now let your eyes close, and let's begin our descent into the twilight. The Mesopelagic zone exists in a space between worlds. Above it lies the Epelagic zone, the sunlit surface layer where photosynthesis happens, and where most of the ocean life we're familiar with resides. Below it stretches the Bathypelagic zone, the midnight realm where no trace of sunlight ever penetrates, and where the pressure becomes crushing. The Mesopelagic occupies the transition between these extremes, and that transitional nature defines everything about it. It is neither fully light nor completely dark. It is neither warm nor freezing. It is a gradient, a spectrum, a place of in-betweens. Scientists define this zone by light. It begins at the depth where only 1% of surface light remains, which typically occurs around 200 meters down in clear ocean water, though it can be shallower in murky coastal areas or deeper in the crystalline waters of the open ocean. At this depth, the light that filters down is almost entirely blue because water absorbs the longer wavelengths first. Reds and oranges disappear within the first few meters. Yellows and greens fade by the time you reach 100 meters. By 200 meters, what little light remains is a deep, eerie blue that grows dimmer with every meter of descent. This faint illumination creates what scientists call the dysphotic zone, from the Greek words meaning poorly lit. It's enough light to see by, if you have the right eyes, but not nearly enough for plants to photosynthesize. No photosynthesis means no phytoplankton, no seaweed, no marine plants of any kind. The entire ecosystem must rely on food that either drifts down from above or is brought down by the creatures that migrate between the surface and these depths each night. It's an ecosystem built on borrowed energy, on the scraps and migrations from the world above, yet it teems with more life than researchers once thought possible. The lower boundary of the Mesopelagic zone is marked by the complete absence of light. This occurs at roughly 1,000 meters in most ocean waters, though again local conditions can shift this boundary up or down. At 1,000 meters, you are deeper than the height of most mountains you could climb in a day. The pressure at this depth is about 100 times what we experience at sea level. Every square inch of your body would feel the weight of 100 atmospheres pressing inward. For humans, this would be instantly fatal without protection. For the creatures that live here, it's simply home. Temperature in the Mesopelagic zone follows a gradual decline. Near the upper boundary, water temperatures might hover around 15 to 20 degrees Celsius in temperate waters, similar to a cool swimming pool. But as you descend, The temperature drops steadily. By the time you reach the lower boundary at 1,000 meters, temperatures have usually fallen to about 4 to 5 degrees Celsius, roughly the temperature inside a refrigerator. This cold is constant and unchanging. There are no seasons here, no warm summer days or cold winter nights. The twilight zone exists in permanent coolness, insulated from the surface world by hundreds of meters of water. This temperature stratification creates layers within the ocean, zones where water of different temperatures and densities meet and mix slowly. These thermoclines, as they're called, can act as boundaries that some organisms prefer not to cross. They create invisible barriers in the water column, dividing the ocean into distinct neighborhoods. But during the daily vertical migrations, countless creatures cross these boundaries twice each day, swimming through temperature changes that would send a human into shock, adapted through millions of years of evolution to handle these shifts with ease. Oxygen levels in the Mesopelagic zone tell another important story. In many parts of the ocean, this zone contains what's called an oxygen minimum layer, or OMZ. This occurs because organic matter sinking from the surface consumes oxygen as it decomposes, and there's no photosynthesis happening at these depths to replenish it. The oxygen gets used up faster than ocean circulation can replace it. In some regions, particularly in the eastern Pacific and northern Indian Ocean, these oxygen minimum zones become so depleted that only specially adapted organisms can survive. Creatures living in these areas have evolved remarkably efficient metabolisms, able to extract every molecule of oxygen from the water around them. The Mesopelagic zone is enormous in scope. It wraps around the entire planet, existing beneath every ocean and sea deep enough to contain it. It covers roughly 60% of Earth's surface and makes up about 20% of the ocean's total volume. To put that in perspective, the Mesopelagic zone contains more space than all the terrestrial ecosystems on land combined. It's larger than all the forests, grasslands, deserts, and tundras put together. And yet, until recently, we knew almost nothing about what lived there or how the ecosystem functioned. It was simply too deep to be easily accessible, too dark to be observed from the surface, and too remote to study with traditional fishing nets and sampling equipment. When you imagine the ocean, you probably picture waves crashing on beaches, or coral reefs bursting with color, or perhaps the deep, dark abyss of the ocean floor. But the Mesopelagic zone is none of these things. It's the vast middle region, the ocean's true heart, and it's a world unto itself. It's a place where bioluminescence creates living constellations in the darkness, where creatures transparent as glass drift through the gloom, where the largest migration of animals on Earth happens every single day, unseen by human eyes, driven by instincts older than language, older than consciousness itself. As we continue our journey tonight, we'll explore this twilight realm in detail. We'll meet the creatures that call it home, learn about the strategies they use to survive, and discover why this hidden layer of ocean might be more important to our planet's health than almost any other ecosystem. But for now, just let yourself imagine it. Picture a vast dark sea extending around the entire world, filled with lights that blink and flash like stars, where creatures rise and fall through hundreds of meters each day, where the cold water presses in from all sides, and where life has found ways to thrive that challenge everything we thought we knew about biology. This is the Twilight Zone, and we're only just beginning to understand its secrets. Light in the Mesopelagic zone is not like light anywhere else. When you stand on the beach and look at the ocean, sunlight sparkles off the waves, bright and warm. Beneath the surface, in the first few meters of water, light still feels familiar. You can see colors, you can distinguish shapes easily.
Yeah, fish cast shadows, but as you descend, everything changes.
The ocean absorbs light selectively, filtering it wavelength by wavelength, until what remains is transformed into something strange and alien. The first colors to vanish are the reds and oranges. These long wavelengths get absorbed within the top 10 meters of water. This is why blood appears green underwater, and why red fish and crabs look black at depth. There simply isn't any red light left to reflect off their bodies. By the time you reach 50 meters, yellows have faded substantially. Greens disappear by about 100 meters. What this means is that the deeper you go in clear ocean water, the more the world takes on a monochromatic blue cast, as if you're looking through an increasingly dark blue filter. By 200 meters, where the Mesopelagic zone typically begins, only about 1% of surface sunlight remains. This is roughly equivalent to the light level you'd experience at dusk on a clear evening, just after the sun has set, but before full darkness falls. You can still see shapes and movement, but colors are muted, details are unclear, and the overall feeling is one of dimness and shadow. For us, this would be nearly dark. For creatures with eyes adapted to these conditions, it's still bright enough to navigate, hunt, and communicate. The quality of this light changes throughout the day, of course. At midday, when the sun is directly overhead, more light penetrates to the Mesopelagic zone than at dawn or dusk. On cloudy days, less light makes it through. During a full moon, some additional illumination can reach the upper portions of the zone at night, though the effect is minimal. These subtle variations in light level have profound impacts on the behavior of the creatures living here. Many species time their vertical migrations precisely to the light levels they're most comfortable with, ascending as the surface darkens and descending as dawn approaches, always staying within their preferred range of illumination. As you continue descending through the Mesopelagic zone, the light continues to fade. By 500 meters, you're in what most humans would consider total darkness. At this depth, only about 1/10,000th of surface sunlight remains. To our eyes, this would be pitch black, indistinguishable from the depths below. But some fish living here have eyes so sensitive that they can still detect this infinitesimal amount of light. They use it to orient themselves, to distinguish up from down, to see silhouettes of prey or predators passing between them and the faint glow above. By the time you reach 1,000 meters, at the lower boundary of the Mesopelagic zone, sunlight has been completely extinguished. From this point downward, the only light comes from bioluminescence, from the living creatures themselves. It's a boundary as clear as any wall, the transition from a world where the sun's influence, however faint, can still be felt, to a realm of permanent midnight, where the sun might as well not exist. The optical properties of water also create interesting phenomena in the twilight zone. Water is not just darker at depth, it's also clearer in some ways. The upper ocean is full of suspended particles, plankton, and organic matter that scatter light and reduce visibility. In the Mesopelagic zone, there are fewer particles, so in theory, visibility is better for the amount of light available. Predators and prey engage in a constant arms race of detection and camouflage in this dimly lit realm. Every small advantage in seeing or not being seen can mean the difference between life and death. The human eye is simply not equipped for the Mesopelagic zone. Our eyes evolved to work in bright daylight, and while we can adapt to low light conditions, we can't come close to matching the visual sensitivity of creatures that have evolved for millions of years in twilight. Many mesopelagic fish have eyes that are proportionally larger than almost any other vertebrate. Some have tubular eyes, shaped like cylinders that point upward, maximizing their ability to detect faint downwelling light and the silhouettes of prey swimming above them. Others have developed special visual pigments that are tuned to the narrow band of blue light that penetrates to these depths, making them incredibly efficient at capturing whatever photons are available. Some species have even developed multiple visual systems. Certain dragonfish, for example, have evolved the ability to produce red bioluminescence, which most other deep-sea creatures cannot see. They use this as a kind of private searchlight, illuminating prey without the prey knowing they're being watched. It's like having night vision goggles in a world where everyone else is colorblind. This kind of adaptation shows just how intense the competition for survival is in the twilight zone, and how evolution finds the most creative solutions to the challenges of life in permanent dimness. The intensity and quality of light in the Mesopelagic zone also varies geographically. In the clear blue waters of the open ocean, light penetrates deeper and stays blue for longer. In coastal waters, where rivers dump sediment and nutrients, the water is murkier, and the twilight zone effectively begins at shallower depths. Near the equator, where the sun is more directly overhead, more light reaches greater depths than at higher latitudes. These geographic variations mean that the Mesopelagic zone is not uniform around the world. A creature at 300 meters depth in the crystal clear waters of the mid-Pacific might experience more light than a creature at 200 meters in the turbid waters off a major river delta. Scientists study light in the Mesopelagic zone using specialized instruments called radiometers that can detect incredibly faint levels of illumination. These instruments have revealed that the light environment at depth is far more complex than we once imagined. There are layers where light changes rapidly, zones where it remains relatively constant, and even times when brief bursts of bioluminescence from startled animals create temporary flashes brighter than the ambient sunlight. The twilight zone is not a static place. It's a dynamic environment where light levels shift and flow, where day and night create different conditions, and where life has adapted to every subtle variation. For a creature living in the mesopelagic zone, light is information. The direction of faint illumination tells you which way is up. The intensity tells you what time of day it is, and whether it's safe to migrate toward the surface. The patterns of bioluminescent flashes tell you where other creatures are, what species they might be, and whether they're potential mates, rivals, or threats. In this world of perpetual twilight, light becomes a language, a navigation tool, a weapon, and a means of survival. And for us, lying here in the darkness of our own rooms, trying to imagine what it would be like, it's a reminder that our experience of the world is just one of countless ways that life can perceive and interact with the environment. In the twilight zone, darkness is not the absence of light. It's a different kind of presence, a different way of seeing, and a different way of living. In the permanent dimness of the mesopelagic zone, countless creatures have evolved a remarkable ability that seems almost magical. They can make their own light. This phenomenon, called bioluminescence, is one of the most widespread adaptations in the twilight zone. Scientists estimate that up to 90% of the animals living in these depths possess some form of light-producing capability. It's not just common, it's nearly universal, and it serves purposes that range from the mundane to the extraordinary, from simple survival to complex communication. Bioluminescence works through a chemical reaction. Most bioluminescent organisms produce light when a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase. This reaction releases energy in the form of light, usually with minimal heat, making it an incredibly efficient process. Different species use slightly different versions of these chemicals which produce different colors of light, though most bioluminescence in the ocean glows blue-green. This wavelength travels farthest through seawater and is the color most organisms are best adapted to see. It's the color of twilight itself, amplified and turned into a tool. Some organisms produce their own bioluminescent chemicals internally, synthesizing luciferin and luciferin and luciferin and luciferin in specialized organs called photophores. These light organs can be as simple as a patch of glowing cells or as complex as a structure that resembles a flashlight, complete with a lens to focus the light, a reflector to direct it, and shutters that can cover or reveal it at will. The variety and sophistication of these organs is stunning. Some fish have hundreds of photophores arranged in specific patterns along their bodies. Each pattern is unique to a species, possibly serving as a form of identification, letting individuals recognize others of their kind in the darkness. Other organisms take a different approach. Instead of making their own light, they culture bioluminescent bacteria in specialized pockets within their bodies. The bacteria produce light continuously, and the host organism controls when and how much light is visible by covering or uncovering the bacterial light organs. This symbiotic relationship benefits both parties. The bacteria get a safe home and a steady supply of nutrients, while the host gets a built-in lighting system without having to spend energy producing the chemicals itself. It's an elegant solution, and it's found in numerous species throughout the mesopelagic zone. One of the most important uses of bioluminescence is counterillumination, a form of camouflage that's unique to the ocean's dimly lit zones. The principle is simple but brilliant. If you're a small fish or squid swimming in the twilight zone, predators below you can see your silhouette against the faint downwelling light from the surface. You appear as a dark shape against a slightly less dark background. But if you have photophores on your underside that produce light matching the intensity and color of the light coming from above, you can effectively erase your shadow. To a predator looking up, you seem to disappear, blending seamlessly with the background glow. Many species have evolved incredibly sophisticated counter-illumination systems. Some can adjust the brightness of their ventral photophores in real time to match changing light levels as they rise or fall through the water column. Others have different photophores for different depths, each tuned to a specific light intensity. And some can even adjust the angle at which their light is emitted to account for the direction of sunlight filtering down from above. It's a complex, dynamic form of camouflage that requires constant adjustment and represents millions of years of evolutionary fine-tuning. Bioluminescence also plays a crucial role in predation. Some creatures use it to attract prey, the most famous example being the anglerfish. Female anglerfish have a modified dorsal fin spine that extends forward over their heads like a fishing rod, and at the end of this rod is a bioluminescent lure. The lure glows softly in the darkness, looking like a small organism or perhaps a bit of food. Curious fish approach to investigate, and the anglerfish's mouth, which can be enormous relative to its body size, suddenly gapes open and sucks the prey inside. It's ambush predation taken to an extreme, using light as the bait in a deadly trap. Other predators use bioluminescence more actively. Certain species of dragonfish have photophores arranged around their eyes or on stalks extending from their chins. They use these lights like searchlights, scanning the water for prey. As mentioned earlier, some dragonfish have even evolved the ability to produce red bioluminescence, which most other deep-sea creatures cannot see because their eyes are optimized for blue light. This gives these dragonfish a secret weapon. They can see prey that cannot see them or their light. It's an evolutionary innovation that highlights just how competitive life in the Twilight Zone can be. Bioluminescence can also serve as a defense mechanism. When attacked or threatened, some small crustaceans and squid squirt out clouds of bioluminescent material. This acts like a biological smoke bomb, creating a glowing decoy that confuses the predator while the prey escapes into the darkness. The predator, momentarily blinded by the flash of light or distracted by the glowing cloud, loses track of its target. Other organisms produce flashing lights when disturbed, possibly to startle predators or to attract the attention of even larger predators that might pose a threat to the initial attacker. In this scenario, the bioluminescence functions almost like a burglar alarm, calling for help from higher up the food chain. Communication is another important function of bioluminescence. In the vast dark expanses of the Mesopelagic zone, finding a mate can be incredibly difficult. Population densities are low, visibility is limited, and moving around burns precious energy. Bioluminescent signals offer a solution. Many species have distinctive patterns of photophores that act like species-specific badges or signals. Males and females of the same species might have different patterns, allowing them to identify potential mates from a distance. Some species engage in elaborate bioluminescent displays, flashing or glowing in specific rhythms that might communicate readiness to reproduce, territorial boundaries, or other information important for survival and reproduction. The patterns of photophores on some fish are so distinctive that scientists can identify species just by looking at where the lights are arranged. It's like each species has its own constellation painted on its body. These patterns have been shaped by millions of years of evolution, refined through natural selection until they serve their purpose with maximum efficiency. For a species that might only encounter another member of its kind rarely in the vastness of the ocean, having a clear, unmistakable signal of identity is crucial. Studying bioluminescence in the Mesopelagic zone is challenging. These organisms are fragile, and many can't survive being brought to the surface. The change in pressure, temperature, and light can damage or kill them before scientists have a chance to observe their natural behavior. When brought up in nets, many species lose their bioluminescent capability or can't display it properly in the stressful conditions of a shipboard aquarium. To truly understand how these creatures use light, researchers have had to develop new technologies: deep-diving submersibles, remotely operated vehicles equipped with cameras sensitive to low light levels, and specialized equipment that can observe animals in their natural habitat without disturbing them. Some of the most spectacular footage of mesopelagic bioluminescence has come from researchers who simply turned off all their lights and waited. In the complete darkness, the Twilight Zone reveals itself as a realm of living stars. Tiny copepods flash like sparks when disturbed. Jellyfish pulse with rhythmic glows. Squid communicate with complex displays that ripple across their bodies. Fish become constellations swimming through the night. It's a light show that happens every moment of every day in the ocean's twilight realm, unseen by most of the world, a private performance for an audience of predators and prey. For us, lying here in the darkness of our rooms, it's worth taking a moment to think about what bioluminescence represents. In a place where sunlight fails, life created its own light. In a realm of scarcity and competition, organisms found ways to use chemistry to communicate, to hunt, to hide, and to find each other in the vastness. It's a testament to the creativity of evolution, to the sheer persistence of life in finding solutions to every challenge, no matter how extreme the environment. The Twilight Zone teaches us that darkness is not empty. It's filled with light of a different kind, light that comes from within, light that speaks and signals and illuminates the hidden patterns of existence in one of the most remarkable ecosystems on our planet. The fish of the Mesopelagic zone are unlike any you might see in an aquarium or catch from a boat. They have evolved in an environment where food is scarce, light is dim, and the pressure is immense. Their bodies reflect these challenges, shaped by millions of years of natural selection into forms that are sometimes beautiful, sometimes bizarre, and always perfectly adapted to life in the twilight. Perhaps the most abundant vertebrate on Earth is a fish most people have never heard of, the bristlemoth. Scientists estimate there may be quadrillions of bristlemoths living in the Mesopelagic zone, making them potentially more numerous than any other fish species on the planet. They're small, usually just a few inches long, with large mouths full of tiny needle-like teeth. These teeth give them their common name. Despite their modest size and unassuming appearance, bristlemoths play an enormous role in the Twilight Zone ecosystem. They feed primarily on copepods and other small zooplankton, converting the energy of these tiny creatures into their own biomass, which in turn feeds larger predators. In many ways, bristlemoths are the foundation of the mesopelagic food web, the link between microscopic life and the larger animals that humans care about. Bristlemoths are divided into several species, and different species occupy different depths and regions. Some perform daily vertical migrations, rising toward the surface at night to feed and descending to deeper water during the day to avoid predators. Others remain at depth constantly, adopting a sit-and-wait strategy that conserves energy. These non-migrating bristlemoths have smaller, less muscular bodies than their migrating relatives. Their swim bladders, the gas-filled organs that help fish control their buoyancy, are filled with fat rather than air. This makes them less capable of rapid depth changes, but also less energetically costly to maintain. It's a trade-off, one of many that species in the Twilight Zone must make to survive in an environment where every calorie counts. Another incredibly abundant group of mesopelagic fish are the lanternfish, family Myctophidae. There are over 250 species of lanternfish, and collectively they may represent one of the largest biomasses of fish in the ocean. Like bristlemoths, lanternfish are generally small, most measuring between 2 and 6 inches in length, but what they lack in size, they make up for in numbers and adaptability. Lanternfish are found in every ocean, from tropical waters to the polar regions, occupying depths from about 200 meters down to sometimes more than 1,000 meters. The name lanternfish comes from the numerous photophores that dot their bodies. These light organs are arranged in specific patterns that vary by species, creating unique signatures that help individuals identify members of their own kind in the darkness. The photophores serve multiple purposes: counter-illumination to avoid predators, species recognition, and possibly communication. Some lanternfish have additional specialized photophores, including ones near their eyes that may help them see prey or navigate. Most lanternfish are active migrants, participating in the daily vertical migration that we'll explore more deeply soon. They spend their days in the darker depths of the Mesopelagic zone, conserving energy and avoiding visual predators. As darkness falls on the surface, they begin an upward journey of hundreds of meters to feed in the more productive waters near the surface. This journey, repeated twice daily by billions of individual fish, represents an enormous transfer of energy and nutrients between different layers of the ocean. When lanternfish are eaten by larger predators at depth, they effectively transport food from the surface down into the Twilight Zone. When they excrete waste products after feeding, they contribute to the rain of organic matter that sustains deeper communities. Hatchetfish are another characteristic group of mesopelagic fish, named for their distinctive body shape. When viewed from the side, a hatchetfish looks like a blade, thin and deep with a sharp belly. This unusual shape serves a purpose. Hatchetfish have large, tubular eyes that point upward, allowing them to scan the water above for prey silhouettes against the faint downwelling light. Their flat profile, when viewed from below, presents a minimal silhouette, making them harder for predators to spot. Combined with their ventral photophores for counter-illumination, hatchetfish are masters of camouflage in the vertical dimension, nearly invisible both to predators below and prey above. The Twilight Zone is also home to some truly fearsome predators. Despite the small size of most residents, viperfish are among the most striking, with elongated bodies and fangs so large they don't fit in the mouth when it's closed. These teeth are hinged, allowing the viperfish to open its mouth extraordinarily wide to engulf prey that might be nearly as large as itself. Like many mesopelagic predators, viperfish have photophores along their bodies and a bioluminescent lure to attract prey. They are also vertical migrators, following their prey toward the surface at night. Dragonfish are another group of predators that seem designed to inhabit nightmares. Various species of dragonfish live in the Twilight Zone, but they share common features: elongated bodies, large teeth, and bioluminescent capabilities. Some have barbels, chin-like appendages that dangle below their mouths, often tipped with bioluminescent lures. These barbels can be moved to mimic the movements of small prey, attracting curious fish within striking range. Female dragonfish can be significantly larger than males, sometimes 10 times the mass. This extreme sexual dimorphism is found in many deep-sea species, possibly because females need more energy reserves for producing eggs in an environment where food is unpredictable. Fangtooth fish, despite their terrifying name and appearance, are actually quite small, usually only about 6 inches long. But relative to their body size, they have the largest teeth of any fish in the ocean. Their fangs are so large that special sockets in the skull allow the teeth to fit when the mouth is closed. Fangtooth live primarily in the Twilight Zone and deeper, where they feed on whatever prey they can find. Younger fangtooth look quite different from adults and were once thought to be a separate species. They have lighter coloration, larger eyes, and less developed teeth. As they mature, they undergo a remarkable transformation, their teeth elongating and their bodies darkening until they take on the adult form. Many mesopelagic fish have unusually large eyes relative to their body size, an adaptation to maximize light collection in the dim environment. Some eyes are tubular, shaped like cylinders rather than spheres. These tubular eyes are fixed in position, unable to move in their sockets, but they provide excellent binocular vision in the upward direction. The lenses in these eyes are often large and sensitive, containing special proteins that focus the tiny amounts of available light onto the retina with minimal distortion. The retinas themselves are packed with rod cells, the photoreceptors that work in low light, with few or no cone cells for color vision. In the blue twilight, color vision isn't particularly useful, so evolution has optimized these eyes for sensitivity over discrimination. Other adaptations in mesopelagic fish include soft, watery bodies that reduce their weight and make them neutrally buoyant with less energy expenditure. Many species have reduced skeletons with thin, flexible bones rather than the heavy, calcified bones of surface fish. Their muscles are often flabby and weak by surface standards, but they don't need powerful swimming muscles in an environment where quick bursts of speed are less important than efficiency. Some species have transparent bodies, making them nearly invisible in the water. This transparency is most common in larval and juvenile fish, and many lose it as they mature, but in the mesopelagic zone, even adults of some species retain a ghost-like translucency. Metabolism in mesopelagic fish tends to be slow. With food scarce and temperatures cold, there's no advantage to a fast metabolism. Many species grow slowly, reproduce infrequently, and live surprisingly long lives for such small fish. Some mesopelagic fish may live for a decade or more, surviving year after year in the permanent twilight, riding the currents, rising and falling with the daily rhythm of migration, feeding when food is available and enduring when it's not. It's a life of patience and efficiency, a strategy perfected over millions of years in one of the most challenging environments on Earth. While fish dominate much of the Twilight Zone, they share the water with an incredible diversity of invertebrate life. These creatures, many of them gelatinous and transparent, drift through the mesopelagic like living glass sculptures, their bodies adapted in remarkable ways to the challenges of life in permanent dimness. Jellyfish are abundant throughout the mesopelagic zone. Unlike the familiar jellyfish you might see washed up on a beach, many deep-sea jellyfish are specialized for life in low light. Some are bioluminescent, producing flashes or steady glows that may serve to startle predators or communicate with other jellyfish. One of the most spectacular is the Atolla jellyfish, sometimes called the alarm jellyfish. When disturbed, Atolla produces a rotating display of bioluminescent light, like a living alarm beacon. Scientists believe this light show might attract larger predators to the area, predators that would pose a threat to whatever disturbed the jellyfish in the first place. It's a clever defense, call for help from something bigger than your attacker. Many deep-sea jellyfish are deep red or purple in color. In the blue light of the mesopelagic zone, Red pigments absorb all available light and appear black, making these jellyfish nearly invisible. Their red coloration also camouflages their stomachs. When a red jellyfish eats bioluminescent prey, the light from the prey's photophores would normally shine through the predator's transparent body, revealing its position. But if the stomach is red, it absorbs the light, keeping the predator hidden. It's yet another example of the arms race between predator and prey in the Twilight Zone, where even the color of your internal organs can determine survival. Comb jellies, or ctenophores, are another group of gelatinous creatures common in these depths. Though they resemble jellyfish, they're actually a completely different phylum, more distantly related to jellyfish than jellyfish are to us. Comb jellies get their name from the rows of beating cilia that run along their bodies. These cilia, which look like tiny combs, beat in coordinated waves to propel the animal through the water. When light hits them, they create rainbow-like iridescence, one of the few splashes of color in the blue twilight. Most comb jellies are predators, using sticky tentacles or large, engulfing mouths to capture small prey. They range in size from millimeters to over a meter in some species, and they play important roles as both predators and prey in the mesopelagic food web. Squid are among the most sophisticated inhabitants of the Twilight Zone. Unlike their gelatinous neighbors, squid are active swimmers with well-developed nervous systems, complex eyes, and elaborate behaviors. Numerous species of squid inhabit the Mesopelagic, ranging from thumb-sized juveniles to the legendary giant squid, which can grow longer than a school bus. Most mesopelagic squid are far smaller than the giants, but they're no less remarkable. Many have photophores arranged in complex patterns across their bodies. Some can control these photophores individually, creating intricate displays of light that might be used for communication, camouflage, or courtship. The vampire squid, despite its name, is actually quite harmless. It's a small cephalopod, usually less than a foot long, that lives in the oxygen minimum zones of the Mesopelagic. Its scientific name, Vampirocheuthis infernalis, means vampire squid from hell, given for its dark coloration and the web of skin connecting its arms, which gives it a cloak-like appearance. When threatened, the vampire squid can pull this web cloak over itself, creating a defensive posture that resembles a spiky ball. It also has the lowest metabolic rate of any cephalopod, an adaptation to life in low-oxygen water. Rather than hunting live prey like most squid, the vampire squid feeds on marine snow, the detritus drifting down from above. It uses specialized filaments to collect this material, then scrapes it off with its beak. It's a feeding strategy rarely seen in cephalopods, but perfect for an environment where oxygen is limited and active. Hunting would be too costly. The strawberry squid is another Twilight Zone specialist with remarkable adaptations. It has two eyes of completely different sizes and functions. The larger left eye points upward and is designed to detect faint silhouettes of prey against the surface light. The smaller right eye points downward and is specialized to see bioluminescent flashes in the darkness below. This asymmetry allows the squid to effectively monitor two different environments at once, maximizing its ability to find food and avoid becoming food itself. Its body is covered with photophores that provide counter-illumination, and it can change color to some degree, another tool in its survival arsenal. The Twilight Zone is also home to countless smaller invertebrates that form the foundation of the food web. Copepods are tiny crustaceans, most smaller than a grain of rice, that feed on even smaller particles and microorganisms. They exist in enormous numbers, and many species migrate vertically every day. These migrations are the primary fuel for the daily vertical migration phenomenon we'll discuss soon. When billions of copepods rise to feed at night, they attract the fish that feed on them, which in turn attract larger predators. It's a cascade of movement and energy that ripples through the entire ecosystem. Krill, larger cousins to copepods, are also abundant in some regions. These shrimp-like crustaceans can grow to several inches in length and form massive swarms that darken the water. Many krill species live primarily in the Twilight Zone, migrating up to feed at night. They're an important food source for fish, squid, seabirds, and even some whales. Their photophores help them stay in contact with other members of their school and may also provide counter-illumination. The oil-rich bodies of krill make them energy-dense food, and predators that can find and exploit krill swarms have hit a nutritional jackpot. Salps are another gelatinous group worth mentioning. These transparent barrel-shaped creatures, are actually more closely related to vertebrates than to jellyfish, believe it or not. They're tunicates, primitive chordate relatives that pump water through their bodies, filtering out phytoplankton and other small particles. Salps can exist as individuals or form long chains where multiple individuals are connected. These chains can extend for dozens of feet, swimming through the water in coordinated movements. Like many Twilight Zone organisms, salps migrate vertically, though their migrations may be more passive than active, drifting with currents that shift at different times of day. Siphonophores represent some of the most bizarre creatures in the ocean. They look like single animals, but are actually colonies of specialized individuals called zooids, each performing specific functions for the colony. Some zooids handle feeding, others reproduction, others locomotion. Together, they function as a single organism. Some siphonophores form long, string-like chains that can extend over 100 feet, making them among the longest animals on the planet. They trail tentacles lined with stinging cells to capture prey, and many are bioluminescent. In videos taken by deep-diving vehicles, siphonophores appear as delicate glowing strings spiraling through the darkness, beautiful and deadly in equal measure. The invertebrate life of the Mesopelagic zone represents an incredible diversity of forms and strategies, from the simplicity of a drifting comb jelly to the complexity of a hunting squid. These creatures have filled every available niche in the Twilight realm. They are predators and prey, filter feeders and scavengers, migrants and permanent residents. Together with the fish, they create an ecosystem of staggering complexity, one that we're only beginning to understand and appreciate. Every day, as the sun sets across the world's oceans, something extraordinary begins, deep beneath the surface. In the darkness of the Twilight Zone, countless creatures stir. They're preparing for a journey, a migration that will take them hundreds of meters upward through the water column toward the surface. As darkness falls, they rise, swimming against gravity, ascending from the cold depths into warmer water where food is abundant. Hours later, as dawn approaches, they'll reverse course, descending back to the safety of the twilight. This happens every day, in every ocean, involving more animals by weight than any other migration on Earth. This is diel vertical migration, and it's one of the most important ecological processes on the planet. The word diel comes from the Latin dies, meaning day, and refers to a 24-hour cycle. Diel vertical migration is a daily pattern where organisms move up and down through the water column on a predictable schedule. The scale of this migration is difficult to comprehend. Some estimates suggest that billions of tons of animals participate in diel vertical migration every day. To put that in perspective, that's more biomass than all the humans on Earth, and it's moving hundreds of meters twice daily in response to the rising and setting of the sun. Scientists first discovered diel vertical migration by accident during World War II. Naval vessels equipped with sonar were scanning the depths for enemy submarines when they encountered something unexpected, a thick layer in the water that reflected sound waves, creating a false reading that looked like a seafloor. This deep scattering layer, as it came to be known, appeared at about 300 to 500 meters during the day, but at night, it rose closer to the surface. After ruling out equipment malfunction, researchers eventually realized they were detecting huge aggregations of organisms. The layer was biological, not geological, and it was moving. Further investigation revealed that the deep scattering layer was composed primarily of small fish and zooplankton. During the day, these organisms stayed in the relative safety of the Twilight Zone, where there was enough darkness to hide from visual predators. At night, they rose to the pelagic zone, where phytoplankton was abundant and feeding opportunities were rich. The daily movement created a pulsing layer of life that rose and fell like a living tide. It was eventually recognized as the largest animal migration on Earth, surpassing the famous migrations of caribou across tundra or wildebeest across African plains, at least in terms of sheer biomass. Why do animals undertake this exhausting journey twice every day? The answer lies in a fundamental trade-off between feeding and avoiding predation. The surface waters are rich in food because that's where photosynthesis happens. Phytoplankton convert sunlight and nutrients into organic matter, creating the base of the ocean food web. Small zooplankton feed on phytoplankton, larger zooplankton feed on smaller ones, and small fish feed on both. It's a feast, especially compared to the meager pickings in the Twilight Zone, but it's also dangerous. During the day, visual predators can easily spot and capture prey in the well-lit surface waters. For small, relatively slow organisms, staying at the surface during daylight is often a death sentence. By migrating down to the twilight zone during the day, small fish and zooplankton reduce their risk of predation dramatically. Visual predators like larger fish, seabirds, and marine mammals hunt primarily by sight, and in the dimness of the mesopelagic zone they're far less effective. The migrators pay a price in terms of the energy required to swim hundreds of meters, but they gain safety. At night, when darkness covers the surface, the advantage shifts. Surface predators can no longer see as well, so the risk of predation decreases. The migrators can rise safely, feed in the productive waters, and then return to the depths before dawn exposes them again. The timing of migration is remarkably precise. Most migrating species begin their upward journey shortly after sunset and complete it within an hour or two. They remain in the surface waters for several hours, feeding actively, then begin descending before dawn. By the time the sun rises, they've returned to depth. This timing is controlled by light level, specifically by the rapid decrease in illumination at dusk and the equally rapid increase at dawn. Organisms have internal biological rhythms that are tuned to these light cues, allowing them to anticipate the optimal time to move. Experiments have shown that even when kept in constant low light in laboratory conditions, many migrating species still show rhythmic behavior on a 24-hour cycle, suggesting that an internal clock supplements the external light cues. This internal rhythm ensures that even if conditions at depth make it impossible to detect the faint light from the surface, the animals still know approximately when to begin their journey. It's a backup system, redundancy built into the biological software that governs their behavior. Not all species migrate the same distance or follow the same schedule. Some zooplankton migrate from about 500 meters to less than 50 meters, covering 450 meters twice daily. Others make shorter trips. Some species of fish remain at depth during the day, but only rise to the upper mesopelagic at night, not all the way to the surface. And some organisms do the opposite, engaging in what's called reverse diel vertical migration. These species, often predators that feed on the normal migrators, stay at the surface during the day and descend at night, following their prey into the depths. It's a secondary migration driven by the primary one, showing how interconnected these behaviors are. The energy cost of migration is significant. Swimming hundreds of meters requires fuel, and for animals living in a food-scarce environment, every calorie matters. So why do it? The answer is that the food available at the surface, even for just a few hours, provides more energy than they expend on the trip. It's a net gain, as long as they don't get eaten. Natural selection has fine-tuned this behavior over millions of years, balancing the costs and benefits until the optimal strategy emerged. And that strategy, for countless species, is to rise and feed under cover of darkness, then retreat to the twilight by dawn. The ecological implications of diel vertical migration are profound. This daily movement transfers enormous amounts of energy and nutrients between different layers of the ocean. When animals feed at the surface and then excrete waste at depth, they're effectively pumping organic matter downward. When they're eaten by predators at depth, those predators benefit from food energy that originated at the surface. The migration connects the productive surface waters with the resource-poor twilight zone, redistributing nutrients and supporting communities that would otherwise struggle to survive. Diel vertical migration also plays a crucial role in the global carbon cycle, something we'll explore in more detail soon. But for now, as we imagine these billions of creatures rising and falling through the darkness every single day, it's worth appreciating the sheer scale and coordination involved. This is not a conscious decision. It's not organized or planned. It's the result of countless individual organisms, each following simple rules written into their biology by evolution. And those individual actions add up to one of the largest, most important patterns of animal movement on the planet. In the twilight zone, life moves to a rhythm set by the sun, even though the sun's light barely reaches these depths. It's a dance between light and darkness, safety and hunger, that plays out every day in every corner of the global ocean. Falling through the twilight zone, drifting down from the sunlit waters above, comes a constant gentle rain. It looks like snow, but it's not frozen water. It's marine snow, a mixture of dead organisms, fecal pellets, mucus strands, bits of discarded shells, and tiny particles of organic matter clumping together as they sink. To the human eye, if you could see it, marine snow would look like a sparse blizzard in slow motion, individual flakes tumbling downward through the blue-black water. But to the creatures of the Twilight Zone, marine snow is food, a lifeline from the productive surface to the depths below. Marine snow begins at the surface. Phytoplankton die or are eaten. Zooplankton produce fecal pellets. Salps shed their discarded feeding filters. Fish scales fall off. Mucus webs cast by pteropods to trap food particles break apart. All of this material is denser than water, so it sinks. As it falls, the particles collide and stick together, forming larger aggregates that sink faster. Bacteria colonize these aggregates, breaking down the organic matter and releasing nutrients. Protozoa graze on the bacteria. Larger organisms pick off individual flakes as they drift past. It's a miniature ecosystem on each particle, a microcosm of life carried downward by gravity. The rate at which marine snow sinks varies enormously. Small particles fall slowly, sometimes taking weeks to descend from the surface to the seafloor. Larger, denser aggregates can sink much faster, perhaps 100 meters per day or more. Fecal pellets from large zooplankton and fish are especially important because they sink rapidly, carrying organic matter to depth before it can be fully decomposed or consumed in the shallower waters. This rapid sinking is crucial for the biological pump, the process by which carbon is transferred from the atmosphere to the deep ocean. The biological pump works like this. Carbon dioxide from the atmosphere dissolves in seawater. Phytoplankton at the surface use this dissolved carbon dioxide for photosynthesis, converting it into organic matter, essentially their bodies. When these organisms die or are eaten, their carbon is incorporated into marine snow or into the bodies of animals. When that material sinks or those animals migrate downward, they carry the carbon with them. At depth, the carbon can be stored for long periods, sometimes centuries or millennia, sequestered away from the atmosphere. This process removes billions of tons of carbon from the atmosphere every year, playing a critical role in regulating Earth's climate. Vertical migration supercharges the biological pump. Without migration, organic matter would rely entirely on passive sinking to reach depth. Marine snow falls slowly, and as it falls, much of it is consumed or decomposed before reaching the Twilight Zone. But when zooplankton and fish migrate down after feeding at the surface, they actively transport carbon. They arrive at depth with full stomachs, then digest their food and release it as fecal pellets or respiratory carbon dioxide. This active transport is faster and more efficient than passive sinking. Some estimates suggest that active transport by migrating animals may double the amount of carbon reaching the deep ocean compared to what would sink passively. The scale of this carbon transport is staggering. One study estimated that zooplankton vertical migration alone could increase ocean carbon export by 14% annually. When you add in the contributions from migrating fish and other organisms, the number grows larger. The Twilight Zone acts as a massive carbon sink, a buffer that helps prevent carbon dioxide from building up in the atmosphere. Without the daily migrations and the rain of marine snow, atmospheric carbon dioxide levels would be higher, and global warming would be accelerated. The creatures of the Twilight Zone, most of them smaller than your finger, are helping to regulate the planet's climate. Marine snow is not uniform in composition. Near the surface, it's relatively fresh, rich in proteins and carbohydrates. As it sinks and ages, bacteria and other decomposers consume the most nutritious components, leaving behind more refractory material that's harder to digest. By the time marine snow reaches the lower Mesopelagic or deeper zones, it's been heavily picked over, and what remains is lower in nutritional value. This creates a gradient in food quality with depth. Organisms living in the upper Twilight Zone have access to fresher food than those living deeper. This is one reason why biomass generally decreases with depth, not just because of light, but because of the declining availability and quality of food. Some organisms in the Twilight Zone are specialized to feed on marine snow. The vampire squid, mentioned earlier, is one example. It extends sticky filaments into the water to catch falling particles, then retracts the filaments and scrapes off the collected material. Other species are filter feeders, pumping water through sieves made of bristles or mucus nets to strain out particles. Still others are detritivores, actively searching for and consuming larger aggregates of marine snow. These feeding strategies are less energetically costly than hunting live prey, but they provide less nutrition per unit of food consumed. It's a trade-off, another example of the different survival strategies organisms use in the Twilight Zone. For researchers studying the Mesopelagic zone, understanding the fate of marine snow is crucial. How much material sinks? How fast does it sink? How much is consumed at different depths? How much reaches the deep sea floor? These questions have implications for carbon cycling, nutrient distribution, and the structure of deep-sea ecosystems. But measuring marine snow is difficult. It's delicate and easily disrupted by sampling equipment. Traditional methods, like deploying sediment traps that collect sinking material, give useful data but can't capture the full complexity of the process. Newer approaches use underwater cameras and image analysis to track individual particles as they fall, providing more detailed information about size, abundance, and sinking rates. The connection between the surface ocean and the twilight zone via marine snow and vertical migration creates a tightly coupled system. Changes in surface productivity caused by seasonal shifts, nutrient availability, or climate change ripple down to affect twilight zone communities. A bloom of phytoplankton at the surface can trigger a cascade of effects: more zooplankton feeding on the phytoplankton, more marine snow sinking, more fish migrating up to feed on the zooplankton, more predators following the fish. The system is dynamic, responding to changes in the environment, and the twilight zone sits at the heart of these interactions, receiving energy and nutrients from above and distributing them downward and throughout the ocean's food webs. As we rest here, thinking about marine snow falling through the darkness like an underwater blizzard, it's a reminder that ecosystems are connected in ways we often don't see or appreciate. The breath you exhaled contains carbon dioxide that might someday dissolve in the ocean, be taken up by a diatom, eaten by a copod, incorporated into a fecal pellet, and carried down to the twilight zone by a migrating lanternfish. That's the scale of connection we're talking about. The twilight zone is not isolated from our world. It's part of the same planetary system, playing its role in cycles that affect climate, ocean chemistry, and the distribution of life across the globe. And it does all this quietly, invisibly, in the permanent dimness beneath the waves, a hidden engine driving processes essential to the health of our planet. While the twilight zone is populated primarily by small fish and invertebrates, it does not exist in isolation. Larger predators, some from the surface and some from the depths, venture into the Mesopelagic zone to feed on the abundant life found there. These predators form a vital link between the twilight zone and the broader ocean ecosystem, transferring energy upward in the food web and connecting disparate habitats. Sperm whales are perhaps the most impressive of the twilight zone predators. These massive mammals, which can exceed 50 feet in length and weigh tens of tons, are capable of diving to extraordinary depths. Using specialized adaptations to manage pressure and oxygen, sperm whales routinely descend past the Mesopelagic zone and into the bathypelagic below, reaching depths of over 6,000 feet. They hunt primarily for squid, including large species that live in the twilight zone and deeper. A single sperm whale can consume hundreds of pounds of squid per day, making them significant predators in the deep ocean food web. The ability of sperm whales to hunt in the twilight zone and beyond is remarkable. They use echolocation, producing powerful clicks that travel through the water and bounce back from prey items. By analyzing the returning echoes, sperm whales can locate squid in total darkness, determining their size, distance, and movement. The whales dive on breath holds that can last over an hour, swimming through the cold, dark waters with slow, efficient movements. When they locate prey, they accelerate and use suction to pull squid into their mouths. Then they ascend, returning to the surface to breathe before diving again. It's an energetically demanding lifestyle, but the abundance of prey in the twilight zone makes it worthwhile. Tuna are another group of predators that exploit mesopelagic resources. Several species of tuna, including big-eye tuna and yellowfin tuna, make repeated dives into the twilight zone during the day to feed. These dives can take them several hundred meters down, well into the Mesopelagic. Tuna are warm-blooded, or more accurately, they're regionally endothermic, able to maintain their swimming muscles and organs at temperatures above that of the surrounding water. This gives them a metabolic advantage in the cold depths, allowing them to swim faster and react more quickly than the cold-blooded fish they're hunting. But it also means they burn energy at a high rate, so they must consume large amounts of food to sustain their metabolism. Tuna dives into the twilight zone are often timed to coincide with the deep scattering layer. During the day, when most mesopelagic organisms are at depth, tuna descend to where the prey is concentrated. They may spend minutes to hours at depth, feeding actively, then return to the warmer surface waters to recover. Some studies suggest that tuna use these surface intervals to rewarm their bodies, as the cold water at depth drains heat even from their elevated body temperatures. The pattern of dive, feed, return, repeat continues throughout the day, a strategy that allows tuna to exploit a resource that few other surface predators can access. Swordfish are another major predator associated with the Twilight Zone. These large, fast-swimming fish are found in tropical and temperate waters around the world. Swordfish are also capable of elevating their brain and eye temperatures, which improves their vision and neural processing in cold water. They make deep dives during the day, often descending to 400 meters or more, hunting for squid, small fish and crustaceans. At night, they move to shallower depths, sometimes near the surface, where they continue to feed on organisms that have migrated upward. Swordfish stomachs often contain a variety of mesopelagic prey, including lanternfish and squid, confirming their role as important predators in this ecosystem. Sharks also hunt in the mesopelagic zone. Some species, like the cookie-cutter shark, live primarily at depth but rise toward the surface at night. Cookie-cutter sharks have a unique feeding strategy. They approach larger animals like tuna, dolphins, or even whales, attach themselves with suction-like lips, and use their razor-sharp teeth to carve out a circular plug of flesh. Then they drop away, leaving the victim with a distinctive wound. It's a parasitic form of predation, allowing the small shark to feed on much larger animals without killing them. Other shark species, including some of the bizarre deep-sea sharks with long eel-like bodies, patrol the Twilight Zone constantly, hunting for small fish and invertebrates. Marine mammals beyond sperm whales also use the Twilight Zone. Beaked whales are deep divers that feed primarily on squid and fish at mesopelagic and bathypelagic depths. Some species hold the record for the deepest and longest dives of any mammal. Certain seals and sea lions also make foraging dives into the Twilight Zone, though their dives are typically shallower and shorter than those of whales. Emperor penguins, despite being birds, can dive to several hundred meters to catch fish and squid, making them one of the few avian predators of the Mesopelagic. The importance of mesopelagic prey to these predators cannot be overstated. For many large, commercially valuable fish species, Twilight Zone organisms make up a significant portion of their diet. Tuna, swordfish, and other billfish rely on mesopelagic fish and squid, especially in regions where surface prey is less abundant. This means that the health of Twilight Zone populations directly affects the health of fisheries that humans depend on. If mesopelagic communities are disrupted, it could cascade upward, reducing populations of predators and affecting human food security and ocean economies. Research into predator-prey relationships in the Twilight Zone is ongoing and revealing complex patterns. Scientists use a variety of methods to study these interactions. Stomach content analysis, where they examine what predators have eaten. Stable isotope analysis, which traces the flow of nutrients through food webs. And electronic tagging, where they attach sensors to predators to track their diving behavior and habitat use. These studies have shown that the Twilight Zone is not a marginal habitat for these predators, but a core feeding ground, essential to their survival and reproduction. From the perspective of the Twilight Zone ecosystem, these large predators represent both a threat and a connection. They remove biomass, consuming fish and squid that took energy to produce, but they also connect the Twilight Zone to the surface and to coastal ecosystems. When a tuna feeds on lanternfish at depth and then is caught by human fishers in surface waters, the energy that originated as phytoplankton in the Twilight Zone's food web ends up on a dinner plate thousands of miles away. It's a reminder that ocean ecosystems are not neatly compartmentalized but interconnected across space, depth, and time. As we think about these predators moving through the twilight, hunting in darkness or dim light, we're reminded of the reach of life. Even in the most remote and challenging environments, there are organisms adapted to exploit every resource. The Twilight Zone may be distant and dark, but it's not isolated. It's part of a web that includes surface waters, deep trenches, coastal areas, and even terrestrial systems through the carbon cycle and nutrient flows. Every piece affects every other piece. A global ecosystem in constant motion and flux, sustained by energy from the sun and driven by the adaptations and behaviors of countless organisms, each playing its role in the great dance of life. To survive in the Twilight Zone requires more than just tolerance for cold and pressure. It requires a suite of specialized adaptations, behavioral and physiological, that allow organisms to find food, avoid predators, reproduce successfully, and conserve energy in an environment where every resource is precious. The creatures of the Mesopelagic zone have evolved some of the most remarkable survival strategies found anywhere on Earth, demonstrating the creativity and power of natural selection. Counter-illumination, which we've touched on before, deserves deeper exploration. This camouflage strategy relies on matching the ambient light coming from above. An organism produces light on its underside that mimics the intensity and color of the downwelling sunlight filtering through the water. To a predator looking up, the organism's silhouette disappears against the background. It's an active form of camouflage, requiring the organism to constantly adjust its light output as it moves through different depths or as surface light conditions change. Some species have sensors on their backs that detect the ambient light level and automatically adjust the ventral photophores to match. It's a closed-loop system, continuously calibrating to maintain invisibility. The effectiveness of counter-illumination is remarkable. Studies have shown that fish using this strategy can reduce their detectability to predators by orders of magnitude. A predator that could normally see a silhouette from tens of meters away might not notice a counter-illuminating prey item until it's just meters distant. In an environment where predators and prey are both moving, that difference in detection distance can be the difference between life and death. For a small fish trying to survive long enough to reproduce, counter-illumination is worth the energy cost of maintaining photophores and producing light. Another widespread adaptation is the use of red coloration. Many Twilight Zone organisms are deep red or black. This seems counterintuitive, as red is usually a warning color in nature. But in the blue light of the Mesopelagic zone, red pigments absorb all available light wavelengths. There's no red light to reflect because red light doesn't penetrate this deep. So a red animal looks black, blending into the darkness. This adaptation is particularly useful for predators. A red-colored predator can have a stomach full of bioluminescent prey without that light shining through its body and giving away its position. The red stomach absorbs the light, keeping the predator hidden. Some crabs, shrimp, and jellyfish in the Twilight Zone are brilliant scarlet in color, but in their natural habitat, they're effectively invisible. Eye adaptations in the Twilight Zone are among the most extreme in the animal kingdom. We've already mentioned the large tubular eyes of some fish, but it's worth emphasizing just how specialized these structures are. The eyes of some mesopelagic fish occupy a significant fraction of their head volume, with lenses that are enormous relative to body size. These lenses gather and focus every available photon onto retinas packed with rod cells. Some species have evolved reflective layers behind the retina, called tapetum, that bounce light back through the photoreceptors a second time, effectively doubling the chance of photon capture. It's the same adaptation that makes animal eyes glow in headlights, but in the Twilight Zone, it's an essential tool for survival. Some fish have gone even further. Certain species have divided retinas with different regions specialized for different visual tasks. One part of the eye might be optimized to look upward for silhouettes, while another looks downward for bioluminescent flashes. This division of labor allows the fish to monitor multiple threats and opportunities simultaneously without having to reorient its entire body. And some, like the barley fish with its transparent head, have eyes that are fixed in position but can rotate inside the fluid-filled dome of the skull, giving the fish a wider field of view without the need for external movement. Metabolic adaptations are equally important. Many mesopelagic organisms have exceptionally slow metabolisms, conserving energy in an environment where food is unpredictable. They grow slowly, mature late, and may live much longer than surface species of similar size. A small shrimp in the Twilight Zone might live for 6 years or more, compared to 1 or 2 years for a coastal shrimp. This slow pace of life reduces energy demands, but also means that populations recover slowly from disturbances. If a fish population is depleted by overfishing or environmental change, it might take decades for numbers to rebound, if they rebound at all. Reproductive strategies in the Twilight Zone often involve producing small numbers of large, well-provisioned eggs, rather than the broadcast spawning of millions of tiny eggs seen in many surface fish. The rationale is that in a low-food environment, giving offspring a better starting investment increases their chance of survival. Some species provide parental care, another unusual adaptation for fish. Male anglerfish take this to an extreme. In some species, males are tiny compared to females and permanently fused to the female's body, becoming essentially a parasitic sperm bank. The male receives nutrients from the female's bloodstream and provides sperm when needed. It's one of the strangest reproductive strategies in the animal kingdom, but it solves the problem of finding a mate in the vast dark expanses of the Twilight Zone. Transparency is another adaptation worth noting. Many small organisms in the Twilight Zone are nearly transparent, making them difficult for predators to see. Transparency works well for small animals where structural support is minimal, but it's harder to achieve in larger organisms with complex organs and skeletons. Still, some larger animals retain partial transparency, with only essential organs visible and the rest of the body glass-like. This creates a disembodied, ghostly appearance that can be startlingly effective camouflage. Some Twilight Zone organisms have reduced their buoyancy needs by eliminating gas-filled swim bladders and replacing them with lipid-filled structures, or by having gelatinous, watery bodies. Gas bladders work well at constant depth, but compressing and expanding gas to maintain buoyancy during vertical migration is energetically expensive. By using fats or simply having low-density bodies, these organisms can change depth without the energy cost of managing a gas bladder. It's an elegant solution to a real problem, though it comes with trade-offs. Without a gas bladder, rapid or agile swimming is more difficult, so these species tend to be slower moving and rely on stealth or patience rather than speed. All these adaptations, from bioluminescence to eye structure to metabolic rate, are the products of millions of years of evolution in a unique environment. They're not chosen consciously or designed intentionally. They're the result of trial and error on a vast scale, where natural selection ruthlessly eliminated less effective solutions and preserved the innovations that worked. The creatures we see in the Twilight Zone today are the descendants of the winners in this game, the lineages that cracked the code of survival in one of the most challenging habitats on Earth. And they're still evolving, still adapting, still responding to changes in their environment and to the pressures exerted by predators, prey, and competitors. The Twilight Zone is not a static museum. It's a living laboratory where evolution continues its work every day, shaping life in ways we're only beginning to understand. The Deep Scattering Layer, or DSL, is one of the most striking features of the Mesopelagic Zone, and one of the key pieces of evidence that revealed the scale and importance of diel vertical migration. It's a layer of the ocean that reflects sound waves, creating an echo on sonar equipment. When sonar operators during World War II first encountered it, they thought their instruments were malfunctioning or that they'd discovered an unexpected seafloor feature. But the layer moved, rising toward the surface at night and sinking during the day. Eventually, scientists realized they were detecting enormous aggregations of living organisms, so densely packed that they scattered sound in a way similar to solid ground. The DSL is composed primarily of small fish, especially lanternfish and bristlemouths, along with large zooplankton like krill and shrimp. These organisms have swim bladders, gas-filled organs that help them maintain buoyancy, and it's these swim bladders that scatter sound so effectively. When a sound wave passes through water and encounters a boundary where the density changes, like from water to gas, some of the sound reflects back. A single swim bladder reflects a tiny amount of sound, but billions of swim bladders together create a strong return signal, strong enough to be mistaken for the seafloor. The discovery of the DSL was pivotal for marine biology. It demonstrated that the deep ocean, which many scientists had assumed was relatively barren, actually contained huge quantities of life. It showed that these organisms were migrating on a daily cycle, moving in response to light levels in coordinated, predictable ways. And it provided a tool for studying the Twilight Zone. By deploying sonar at different times and depths, researchers could track the movements of the DSL, estimate its biomass, and begin to understand the ecology of the Mesopelagic region. Modern research vessels use sophisticated acoustic equipment to study the DSL in detail. Multi-frequency sonar can distinguish between different types of organisms based on how they scatter sound at different frequencies. Gas-filled swim bladders, for example, scatter sound very differently than soft-bodied organisms like jellyfish. By comparing the acoustic signatures at various frequencies, scientists can infer the composition of the DSL, determining how much is fish, how much is zooplankton, and even identifying specific species in some cases. This non-invasive method allows researchers to study the Twilight Zone without having to catch and kill organisms, providing better data on populations and behaviors in their natural environment. The DSL is not uniform. It varies in thickness, depth, and composition depending on location, season, and time of day. In some regions, the DSL is a well-defined band of high organism density. In others, it's more diffuse, with organisms spread across a broader depth range. During the day, the DSL typically sits between 300 and 700 meters, though this varies. At night, when organisms migrate upward, the layer can split, with some organisms remaining at intermediate depths while others rise all the way to the surface. This creates multiple scattering layers at night, each composed of different species or life stages with different migration behaviors. The intensity of the DSL signal can be used to estimate biomass by calibrating the acoustic returns against direct measurements from net tows. Scientists can convert sonar data into estimates of how many tons of fish or zooplankton are present. These estimates have revised our understanding of ocean biomass dramatically. Early calculations based on net tows suggested that the Twilight Zone contained perhaps 1 billion tons of fish. Acoustic surveys have suggested the number might be 10 times higher or more. The discrepancy arises because nets are inefficient at catching fast-moving, elusive Twilight Zone fish, and many species avoid nets altogether. Sonar doesn't have this problem. It detects everything in the water column, whether the organisms want to be seen or not. The DSL also plays a role in military operations. Submarine detection relies heavily on sonar, and the presence of a strong scattering layer can interfere with that detection. During the Cold War, navies invested considerable effort into understanding the DSL so they could filter its signal and distinguish submarines from biological scattering. In a way, the Mesopelagic zone became an unintended participant in global military strategy, its inhabitants creating a kind of acoustic camouflage that could hide submarines from detection. Today, the focus has shifted more towards scientific and conservation applications, but the acoustic technology developed for military purposes has been repurposed for studying ocean life. Beyond its practical uses, the DSL is also a reminder of scale. When we think about ocean life, we often picture individual animals, a shark, a whale, a school of fish. But the DSL represents something different. It's a living structure made of billions of individuals, a collective phenomenon that emerges from the behavior of countless organisms. Each fish or shrimp is following simple rules, responding to light, seeking food, avoiding predators. But together, their actions create a layer that spans entire ocean basins, rising and falling in synchrony, a living tide that pulses every day in every ocean around the world. It's one of the most dramatic examples of emergent behavior in nature, where simple individual actions combine to create complex global patterns. For researchers, the DSL is both a tool and a subject of study. It allows them to monitor the health and productivity of the Twilight Zone ecosystem over time. Changes in the depth, intensity, or timing of the DSL can indicate shifts in ocean conditions, climate impacts, or other environmental changes. If warming waters alter the vertical temperature structure of the ocean, the DSL might shift to different depths or change in composition. If overfishing removes top predators, the DSL might become denser as fewer organisms are eaten. By monitoring the DSL over years or decades, scientists can detect changes in the ocean that might not be visible through other methods. The deep scattering layer is a feature unique to the ocean. There's nothing quite like it on land. It's a manifestation of the immense scale and productivity of marine ecosystems, a testament to the abundance of life in regions we rarely see or think about. When we lie here, resting, it's worth picturing that layer. That vast band of life moving through the darkness, rising as we sleep, descending as we wake, part of a rhythm older than civilization, older than humanity, older than most species on Earth. It's a rhythm written into the ocean's biology by the turning of the planet and the rising and setting of the sun, and it continues every night, in waters all around the world, unseen and mostly forgotten, but vital to the functioning of the living ocean. The Twilight Zone, vast and vital though it is, now faces threats that could fundamentally alter its ecosystems. For most of human history, the Mesopelagic zone was too deep, too difficult to access, and too remote to be affected by human activities. But as technology improves and surface fisheries decline, attention is turning to the abundant life of the Twilight Zone as a potential new resource. This has profound implications, not just for the organisms living there, but for the entire ocean and the planet's climate system. The primary threat to the Twilight Zone is potential industrial fishing, as populations of surface fish like tuna, cod, and sardines have been overfished in many regions. Fishing companies are looking for new sources of revenue. The Mesopelagic zone contains an estimated hundreds of millions to billions of tons of fish, primarily lanternfish and bristlenose. This represents a vast, largely untapped resource. Several countries, particularly in Europe, are exploring or have begun trial fisheries targeting these species, with the goal of converting them into fish meal and fish oil for use in aquaculture, animal feed and nutritional supplements. The problem is that we know very little about the biology and ecology of mesopelagic fish. We don't know how fast they grow, how long they live when they reproduce, or how resilient their populations are to fishing pressure. Surface fish species that we've been studying for decades have proven vulnerable to overfishing, with many stocks collapsing under heavy exploitation. Mesopelagic fish may be even more vulnerable because they grow slowly and reproduce infrequently, common traits for deep-sea organisms. If we begin harvesting them at industrial scales before understanding their biology, we risk devastating these populations and causing cascading effects throughout the ocean ecosystem. The ecological consequences of large-scale mesopelagic fishing could be severe. These fish are prey for numerous commercially valuable species, including tuna, swordfish, marine mammals, and seabirds. If mesopelagic populations decline, these predators will have less food, potentially leading to declines in their own populations. This would affect not only ocean ecosystems but also human fisheries and the communities that depend on them. The Mesopelagic zone is not an isolated resource. It's intricately connected to the rest of the ocean food web, and removing large quantities of biomass from it will have ripple effects. There are also climate implications. As we've discussed, the Twilight zone plays a crucial role in the biological carbon pump, sequestering carbon dioxide from the atmosphere and storing it in the deep ocean. Mesopelagic fish are a key part of this process. If fishing reduces their populations, the efficiency of the carbon pump could decline, leaving more carbon dioxide in the atmosphere and accelerating climate change. Some scientists have warned that harvesting the Twilight zone could release carbon that would otherwise be locked away, essentially undoing some of the climate regulation services that the ocean provides. The economic value of catching these fish might be small compared to the environmental cost of disrupting carbon cycling. Mercury accumulation is another concern. Mercury is a toxic heavy metal that enters the ocean from industrial emissions and volcanic activity. It gets converted into methylmercury, a highly toxic form that accumulates in the tissues of marine organisms. Mesopelagic fish, because they live longer and feed at lower trophic levels where mercury concentrations are building up, can accumulate significant amounts of mercury in their bodies. If these fish are harvested and processed into fish meal for animal feed or human consumption, the mercury could enter our food supply. And because mesopelagic fish migrate vertically and are eaten by predators, mercury accumulated in the Twilight zone can be transferred up the food web, affecting larger fish, marine mammals, and ultimately humans. Climate change itself is also affecting the Twilight zone, though in ways we're only beginning to understand. Warming ocean temperatures are altering the vertical temperature structure of the water column, which could affect the depths at which organisms live and migrate. Changes in surface productivity due to shifting ocean currents and nutrient availability will impact the amount of food reaching the Twilight zone in the form of marine snow and migrating zooplankton. Ocean acidification, caused by increasing carbon dioxide absorption, could affect the physiology of some Twilight zone organisms, particularly those with calcium carbonate structures. And deoxygenation, the loss of dissolved oxygen in some regions of the ocean, could expand oxygen minimum zones, making larger areas uninhabitable for species that require even minimal oxygen levels. The combination of these threats, fishing, mercury, climate change, creates a complex and uncertain future for the Twilight zone. Scientists are calling for precautionary approaches, urging governments and industries to pause exploitation until we have a better understanding of these ecosystems and the services they provide. Several international bodies have proposed protections for the Twilight zone, recognizing it as a critical part of the global ocean that deserves conservation. But enforcement is difficult in international waters, and economic pressures to exploit new resources are strong. Conservation of the Twilight zone requires not just scientific understanding, but also political will and public awareness. Most people have never heard of the Mesopelagic zone, and even fewer understand its importance. Raising awareness about this hidden ecosystem, about the remarkable creatures that live there, and the essential roles they play in ocean health and climate regulation, is a necessary first step toward protecting it. We need to value the Twilight Zone, not just for its potential as a resource to extract, but for the services it provides that we cannot easily replace: carbon sequestration, nutrient cycling, support for commercial fisheries, and maintenance of ocean biodiversity. There are also ethical considerations. The creatures of the Twilight Zone are remarkably adapted to their environment, the products of millions of years of evolution. Do we have the right to exploit them before we even understand what they are and how they live? Many species in the Twilight Zone remain undiscovered and undescribed. We could be driving species to extinction before we even know they exist. For some, this is a compelling argument for conservation. The Twilight Zone is a frontier, one of the last great wildernesses on Earth, and preserving it reflects a commitment to humility and respect for the natural world. As we lie here in the darkness of our own rooms, it's sobering to think that the Twilight Zone, so remote and mysterious, is not beyond the reach of human impact. The ocean has often seemed infinite, too vast to be harmed by our activities, but history has shown us otherwise. Fisheries have collapsed, coral reefs have died, ocean chemistry has changed. The Twilight Zone could be next, unless we make deliberate choices to protect it. Those choices require information, which scientists are working hard to gather, and they require action, which depends on individuals, communities, and governments deciding that some places are worth leaving alone, or at least managing with extreme care. The Twilight Zone has existed for millions of years, functioning as a critical part of the ocean system. It deserves the chance to continue doing so for millions more. Studying the Mesopelagic Zone is not easy. It's too deep to observe directly from ships and too vast to sample comprehensively with traditional methods. The creatures that live there are often fragile, sensitive to changes in pressure and temperature, and they behave differently when captured and brought to the surface. For decades, scientists were limited in what they could learn about the Twilight Zone, relying on nets towed at depth to catch whatever organisms happened to swim into them, and on scattered observations from the few submersibles capable of reaching these depths. But technology is advancing, and new tools are beginning to unlock the secrets of the Twilight Zone in ways that were impossible just a few years ago. One of the biggest challenges in studying the Twilight Zone is simply seeing what's there. Traditional nets scare away faster-moving organisms and often damage or kill the creatures they catch, making it difficult to observe natural behavior or even accurate appearances. Many Twilight Zone animals look completely different when alive in their natural habitat compared to how they look after being pulled up in a net. Fragile gelatinous organisms can disintegrate entirely, leaving scientists with little more than a blob of tissue to study. And because nets sample a relatively small volume of water compared to the vastness of the ocean, they can miss rare species entirely or give misleading impressions of abundance. To overcome these limitations, researchers have developed remotely operated vehicles, or ROVs, that can descend to mesopelagic depths and observe organisms without disturbing them. Equipped with high-definition cameras, sensitive lighting, and sometimes manipulator arms for collecting samples, ROVs allow scientists to see the Twilight Zone as it actually is. They can hover in place, following a single animal for minutes or hours to observe its behavior. They can film interactions between predators and prey. They can document bioluminescent displays that would be impossible to see any other way. The footage obtained from ROVs has revolutionized our understanding of Twilight Zone life, revealing species and behaviors that were previously unknown. One particularly innovative ROV is Mesobot, developed by Woods Hole Oceanographic Institution. Mesobot is specifically designed to track individual Twilight Zone organisms over long periods and large distances. It's autonomous, meaning it can operate without a tether to a surface ship, and it's equipped with sensors that allow it to follow a target animal without getting too close and spooking it. Mesobot has successfully followed lanternfish and other species for hours, recording data on their swimming speeds, depths, and behaviors. This kind of information is invaluable for understanding how energy flows through the ecosystem and how animals respond to natural changes in their environment. Acoustic technologies have also advanced significantly. Modern sonar systems can not only detect the deep scattering layer, but can also analyze the signals in sophisticated ways to infer the size, species, and behavior of organisms. Multi-frequency acoustics, as mentioned earlier, uses different wavelengths of sound to distinguish between different types of animals. Scientists can deploy moored acoustic instruments that record continuously for months or years, providing long-term data on migration patterns, seasonal changes, and responses to environmental variations. These datasets are revealing dynamics in the twilight zone that were invisible to earlier snapshot surveys. Another cutting-edge approach is environmental DNA, or eDNA. This technique involves collecting water samples and analyzing the DNA that organisms shed into the water through skin cells, feces, mucus, and other sources. By sequencing this DNA, researchers can identify which species are present in a given area without having to see or catch the animals themselves. eDNA surveys of the Mesopelagic zone have uncovered unexpected diversity, including species that are difficult to sample with nets because they're too rare, too fast, or too fragile. It's a powerful tool for biodiversity assessment. Though it has limitations, it can tell you what species are present, but not how abundant they are or what they're doing. The Ocean Twilight Zone project at Woods Hole Oceanographic Institution represents one of the most comprehensive efforts to study the Mesopelagic zone. Launched in 2018, the project brings together biologists, oceanographers, engineers, and ecologists to tackle fundamental questions about this ecosystem. How much life is there? What species exist? How do food webs function? What role does the Twilight Zone play in climate regulation? The project is developing new technologies, conducting field expeditions in multiple ocean regions, and building models to predict how the Twilight Zone might respond to future changes. It's an ambitious undertaking, but one that's necessary if we're to understand and protect this critical part of the ocean. Despite these advances, there's still so much we don't know. Scientists estimate that only a small fraction of the species living in the Twilight Zone have been formally described. Many organisms observed on camera remain unidentified. Their taxonomy and biology a mystery. We don't understand the full pathways of energy and nutrient flow through these communities. We can't yet predict how changing ocean conditions will affect Twilight Zone ecosystems, or what the consequences of those changes might be for the broader ocean and climate system. In many ways, we're still at the beginning of Twilight Zone science, exploring a frontier that's as vast and alien as any other on Earth. The difficulty of studying the Twilight Zone should not be underestimated. Every expedition requires significant resources, research vessels, expensive equipment, skilled personnel, and time. Weather and sea conditions can delay or cancel plans. Equipment fails in the harsh environment of the deep ocean. Funding for basic research is often limited, competing with other priorities and practical concerns. Yet the scientific community recognizes the importance of this work. The Twilight Zone matters, not just as an intellectual curiosity, but as a critical component of Earth's life support systems. Understanding it is not a luxury, it's a necessity. For those of us lying here, far from the ocean, it might seem abstract, disconnected from daily life. But the Twilight Zone touches us in ways we rarely consider. The fish on our plates may have fed in the Twilight Zone. The carbon dioxide we emit is partially absorbed by processes occurring there. The health of ocean ecosystems, which provide food and livelihoods for billions of people, depends on the productivity and stability of the Twilight Zone. We are all stakeholders in its future, whether we know it or not. And the scientists working to understand it are doing so on behalf of all of us, piecing together the puzzle of how this hidden ecosystem functions and why it matters. As we drift towards sleep, we can appreciate the dedication and ingenuity required to explore the Twilight Zone. It's not easy, but it's important, and slowly, carefully, the picture is becoming clearer. We're learning about a world that exists in permanent dimness, populated by creatures we're only just beginning to meet, playing roles in global processes that we're only starting to understand. The Twilight Zone is revealing its secrets, one discovery at a time, and each discovery deepens our appreciation for the complexity and interconnectedness of life on Earth. And now, as we near the end of our journey together, it's time to reflect on what we've learned about the Twilight Zone and let these thoughts settle gently into rest. We've descended from the sunlit surface into a realm of perpetual dusk, a vast layer of ocean that wraps around our entire planet. We've met creatures that glow in the darkness, that migrate hundreds of meters every day, that hunt with light or hide with camouflage beyond our imagination. We've seen how marine snow falls like an underwater blizzard, carrying energy and carbon from the surface to the depths. We've learned about the largest animal migration on Earth, a daily movement of billions of organisms that most of the world never sees or thinks about. The Mesopelagic zone is a place of extremes and contradictions. It's vast yet largely unexplored. It's dark yet filled with light, the bioluminescent light of living organisms communicating, hunting, hiding. It's cold and pressurized, yet it teems with life, from the most abundant fish on Earth to rarely seen giants like the giant squid. It's remote, existing hundreds of meters beneath the waves, yet it's intimately connected to the surface world and to our own lives through food webs, carbon cycles, and climate regulation. We've learned that the Twilight Zone is not a barren wasteland, but a productive ecosystem, possibly containing more fish biomass than all the rest of the ocean combined. We've seen how creatures have adapted to this environment in remarkable ways, evolving solutions to the challenges of finding food, avoiding predators, and reproducing in a place where resources are scarce and potential mates are hard to find. These adaptations, from tubular eyes to counter-illumination, from red coloration to slow metabolism, demonstrate the power and creativity of evolution, the ability of life to find a way even in the most challenging circumstances. We've explored the ecological importance of the Twilight Zone, how it supports predators like tuna, swordfish, and sperm whales that are economically and ecologically significant. We've seen how diel vertical migration connects different layers of the ocean, transporting energy and nutrients in a daily rhythm that's been ongoing for millions of years. And we've understood the role of the Twilight Zone in the biological carbon pump, how organisms in this layer help sequester carbon dioxide from the atmosphere and store it in the deep ocean, helping to regulate Earth's climate. But we've also confronted the threats facing this ecosystem. Potential industrial fishing could disrupt mesopelagic communities in ways we can't fully predict. Mercury accumulation poses risks to the food web and potentially to human health. Climate change is altering the physical environment of the Twilight Zone, with uncertain consequences for the organisms living there. These threats are real, and they're urgent, but they're not inevitable. With knowledge, care, and foresight, we can choose to protect the Twilight Zone and the services it provides. The Twilight Zone reminds us that our planet still holds mysteries. Even in this age of satellite imaging and instant communication, there are vast regions of Earth that remain largely unknown. The Mesopelagic Zone is one of them, a frontier as challenging to explore as the surface of another planet, yet lying just beneath the waves that lap at our shores. It's humbling to realize how much we don't know, how much remains to be discovered. And it's inspiring to think about the scientists and explorers who are working to uncover these secrets, driven by curiosity, by the desire to understand, and by the recognition that knowledge is the foundation of wise stewardship. For those of us lying here in the darkness of our rooms, drifting towards sleep, the Twilight Zone can feel like a dream, a place too strange and distant to be real. But it is real. Right now, as you rest, creatures are rising through the water column, beginning their nightly migration to feed in the surface waters. Photophores are blinking in the darkness. Marine snow is falling through the cold water. A sperm whale is diving, descending into the blackness to hunt for squid. A lanternfish is using its large eyes to scan the water above for prey. It's all happening, every moment of every day, in oceans around the world. It's part of the living planet we inhabit, a hidden dimension of the biosphere that's as vital as any rainforest or coral reef. We are connected to the Twilight Zone, even if we never see it. The breath we take, the food we eat, the climate we live in, all are influenced by processes occurring in that dark layer of water. The carbon cycle that regulates global temperature depends on the Twilight Zone. The fisheries that feed billions depend on predators that hunt in the Twilight Zone. The ocean's productivity, its ability to support life at all scales from bacteria to whales, is shaped by the movement of organisms through the twilight. We are part of the same system, participants in the same global ecosystem, connected by threads we're only beginning to see. As you let your eyes close, as your breathing deepens and slows, picture the Twilight Zone one more time. Imagine the vast dark waters stretching around the globe. Imagine the creatures drifting and swimming through that space, each one perfectly adapted to its niche, each one playing its role in the ecosystem. Imagine the lights blinking on and off, the slow fall of marine snow, the rise and descent of migrating fish. It's peaceful, in its way. It's a world governed by ancient rhythms, by the sun and the seasons, by hunger and the need to survive, but also by balance, by the intricate connections between species and habitats that have been refined over millennia. The Twilight Zone teaches us about resilience and adaptation. It shows us that life can thrive even in places that seem inhospitable, that evolution can find solutions to any problem given enough time. It reminds us of the interconnectedness of all living systems, how changes in one place ripple outward to affect others, and it invites us to wonder, to be curious, to want to know more about the planet we call home. There is still so much to learn, so much to discover, so many secrets waiting in the depths, and that's a beautiful thing. It means the story isn't over. It means there are still frontiers, still mysteries, still reasons to explore and protect and cherish this remarkable world. So rest now. Let the darkness around you mirror the twilight of the Mesopelagic zone. Let your mind drift like marine snow, gently falling through layers of thought toward the peace of sleep. You've traveled far tonight, descending from the surface into a hidden realm, meeting creatures from another world that's actually our own. You've learned about migrations and adaptations, about food webs and carbon cycles, about the importance of places we rarely see. Carry that knowledge with you into your dreams, knowing that somewhere beneath the waves, the Twilight Zone continues its ancient rhythms, unseen and mostly forgotten, but vital, essential, and endlessly fascinating. If you're still awake enough to hear these words, thank you for joining me on this journey. The Twilight Zone is one of the most remarkable ecosystems on Earth, and I hope you found this exploration relaxing, informative, and perhaps inspiring. If you did, consider subscribing for more deep dives into the hidden wonders of our planet, and if you're able, leave a comment about what surprised you most tonight, or about which creature of the Twilight Zone you'd most like to meet. Until next time, sleep well, dream softly, and remember that even in the darkest places, life finds a way to shine. Good night.